Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, well, we're going to talk about Six Sigma. We're going to talk about world-class engineering, as I like to call it. World-class engineering in your design function. Because people keep talking about what's after Six Sigma, what comes after Six Sigma. I don't understand this question. What comes after world-class engineering? Well, you just make sure that you keep doing world-class engineering. So we are going to talk about world-class engineering. In design. So you might call this Design for Six Sigma if you really wanted to, but because people don't understand what Six Sigma is, people don't understand what a black belt is capable of. They don't understand what black belt training is about. It's about creating a world-class engineer. We're going to call it world-class engineering. So let's use a little example. It's very simple. I'm obviously making up some of these comparisons, some of these examples, simply to show you how powerful Six Sigma could be in a design situation. So we are going to imagine that we are designing an electric motor. Now, in this day and age, there's all sorts of new opportunities for designing electric motors in electric cars and being super efficient in vacuum cleaners and all sorts of things. So suddenly, the good old bog standard electric motor, suddenly we're trying to make it do more, we're trying to make it be more efficient, probably make it cost less, weigh less, all sorts of things. So we're going to look at the idea of a very simple electric motor. So here we've got the we've kind of got the gubbins. We're going to have obviously some copper windings here. So this is the internals. This is the internals of a badly drawn. There's going to be some copper windings going around these cores here. Yeah, so we're trying to design an electric motor, and of course we're trying to get certain things out of it. We're trying to get it to be most powerful. We're probably trying to control the cost. We're probably trying to control the energy consumption. There may be something else, and of course sometimes the designer will say, well, I can get the power but I can't get the cost. I can get the cost but I can't get the energy consumption. And he's trying to hit this sweet spot, and of course he's playing around with his design and he's trying to find the place that keeps everybody happy. Well, what we're going to take a look at, world-class engineering. How would a black belt deal with this? Okay, so here we have the electric motor, and we're going to say that we've sat down with the experts, and the experts have told us, well, look, there are 5 parameters in this electric motor that we tend to move around to move the power, the cost, the energy consumption, etc. And those 5 parameters are, so this is the motor design. And I have no idea, by the way, I've made these parameters up. I have no idea whether these parameters make any difference to the efficiency in an electric motor. But I'm just making this up as an example of what a world-class engineer would do to get new knowledge about his system. Okay, so we've sat down with the experts and they've said this to us, look. Okay, look. The number of coils. Yeah, so the designer can put a number of these coils around the rotor and the stator. How many coils do we actually have? Okay, so the number of coils, and I think they've gone 4 to 6. Not even sure whether that's possible, but anyway, and this is the design space, really important. This is the design space that the designer is saying he's going to work in. Then what we've got is, for each of the coils, we've got the number of turns. Okay, and again, the experts have told us that their design space is between 40 and 60. So that's where they might move the design around. Then what we've got is the wire thickness. So obviously we've got copper wire here. So we've now got the wire thickness. And I think we're going 1 millimeters to 1.2 mil. That's our design space. Then they're going to get clever and they're going to put some silver alloy in the copper that's in the windings, because silver tends to make electricity flow a little bit more. So we're going to put some silver percentage. There's a little alloy. No idea whether you can alloy silver with copper, but anyway, so we're going to go, let's have a think, 1% up to 2%. And obviously that's an expensive thing to do. Putting silver in there is an expensive thing to do. Making it as an alloy instead of just taking pure copper. That's going to be an expensive thing to do on a number of levels. And then finally, we're going to look at the iron core that the copper is wound around. And we're going to look at the density of the iron. So these things are sintered. Let's put that in properly. So the core density, these things are sintered. What have I gone for? 4.4 to 6. Let's have a look. So the core density, 4.4 to 6. Okay. So if you look at this design space, you know, the number of combinations, I'm not quite sure what the number of combinations is here, but we've got 3 times 20, which is 60, times 12, which is 600, 720, 720, plus another 10 here, 720, 7,200, plus another 16, so whatever 7,200 is times 16, well, it's at least 72,000 plus another 40 odd, so it's about, we're talking about 100 approximately. I haven't worked it out properly, but this designer, look, he's literally got 110,000 ways, 110,000 choices as where he could put the design inside that design space. Okay, and he's got to find a sweet spot. So the things that he's interested in measuring coming out of here: power. Okay, what else? Cost, energy consumption. Now that's something else. Let's say torque. Okay, so we got 5 inputs, we got 4 outputs. And now the designer has got to try and optimize this. He's got to try and find the design. Now think about this. He's got 110,000 choices for this system, for this system, for this system, for this system. So there's 500,000 choices approximately. And in amongst those 500,000, there is a sweet spot, potentially, where he might hit all 4 of the targets that someone has set him. Now, it could be that there isn't a sweet spot, by the way. So he could be searching in a space for something that doesn't exist. How about that? And that's where most of the waste is going to come from. He's searching for a solution here for something that doesn't exist. Now, let me show you a world-class engineer. Now, what knowledge have we needed up to now? Well, the experts have told us the design space. They've told us the elements that are important. But now, world-class engineering takes over, because we're not going to expect the expert to be able to guess the solution. What we're going to do is we're going to give this problem, world-class engineering, to a designed experiment. Now, this is exactly the way you should do it. World-class companies, the designers, would do designed experiments, DOEs, day after day after day, probably 2 or 3 of these a day. I don't know how you'd answer this problem any other way. And by the way, your computer can't do this. We are going to do some things here where we're going to choose tolerances. We're going to choose spots in the design where the tolerance can be at the widest. Your computers can never do what we're about to do with a designed experiment. So let's go to the computer, let's look at the pattern, and let's look what a designed experiment would tell you. Okay, so the first thing we're going to do, I'm going to go to my DoE software and I'm going to go create design. And I'm going to create an experiment that will allow me to understand the design space that we've just described. So 5 factors, 5 inputs were what we identified. So if I click next and I click through this menu, it's going to ask me what the 5 are. So at this point I would type in things like the number of coils, and I would put in there 4 and 6. Then I'd put the number of turns, and I'd put 40 and 60, etc. I'm not going to go through all that just to save some time. But if I click next, it says how many responses do you have? Well, we had 4, didn't we? So if I put 4 in there, what it's going to ask me for is 4 pieces of data. And look, I've got a window here where I can actually say what the response is. So power, cost, energy and torque would all be typed in there. Now I'm going to cancel that out because I've already done this. There is the pattern that the experiment wants you to do. Now this is the most efficient pattern. Let me talk about where the pattern is before we look any further at this. Okay, so this pattern, where is it? Well, it's very simple, look. A designed experiment is going to test the design space, and it tests at the extreme of the design space. So this is the design space that your designers have just created by naming those 5 variables. Now I can only draw 3 of the dimensions because I can't draw a 5-dimensional box, but in mathematics 5-dimensional boxes do exist. So if we put the number of coils here, look, so if we go coils and we say, what do we say, 4 to 6, then we went number of turns. So the turns here, and we go, what is it, 40, 60, and then finally back to front we'll go wire thickness. Okay, so wire thickness, and the wire thickness is 1 millimeter at the thin, 1.2 millimeters at the thick. Now then, what's the designed experiment going to do? Well, it's going to do this, look. It's going to ask you to test at the corners. Right, it's going to ask you to test at the corners. Then we fill the box with mathematics, and then we can ask it to hit a sweet spot if a sweet spot exists. Now, by the way, there'd be 4 of these boxes, one for power, one for cost, one for energy, one for torque. And then what you'd ask the computer to do is hit the target, hit 4 targets at the same time. And if it can do it, it will tell you that it can do it, and it will give you the parameters in order to do that. It'll tell you what the design should be. Now that's what a designed experiment is. It's testing at the corners. Now it's a little bit more complicated here because this is 5 variables, so essentially there are 32 corners to test. I can't draw that, but that's what this experiment is doing. So let's go back to the pattern and look what it's asking for next. Okay, so if you look at the pattern now, what I've got, look, is 4 empty sheets. So the first sheet is for the power, the second sheet is for cost, etc. And of course they're empty, because what you're going to do, now this could well be on a computer, so you're not designing 28 motors and putting 28 motors on test. What you're doing is you're working on your computer. Your finite element analysis is doing this work. And then what you would do is you would set the thing up and you would ask for a result out of your finite element analysis. And of course what you've got to do then, populate the table of the results, whatever they come out to. So I've no idea what these things might be. Yeah, so you're going to put all the data in for the power, you're going to put all the data in for the cost. Now obviously if you're doing this on a computer, this is literally 5 minutes work. That's why I'm saying your designer should be doing 3 or 4 DOEs a day, because this is the fastest way to find out how a system works. So imagine now that we've populated all that data for those 4 outputs. So we have 4 pages of data. Now what we want to do is we want to do some analysis. So if I go to Analyze Design, the first thing I'm going to do is some simple graphs. So I'm going to do one for power. I'm going to do one for cost. I'm going to do one for energy consumption. And I'm going to do one for torque. Now, by the way, just something to point out, this table is actually full of random numbers. So the analysis you're seeing is just complete luck of the draw from the random data that's gone into my table. But you can see now from the graphs, let's take a look. So if this was real data, what would it be telling me? Well, this is the torque, and it's saying, look, the number of turns is driving the torque very powerfully. So is the number of coils, so is the thickness of the wire. The silver and the core density has very little effect. Then we look at the energy consumption. So again, look, turns and thickness are driving this thing. Core density is now part of the system. Now I'm looking at, so look at this one, this is cost. So cost, silver happens to be driving the cost, and that's probably true if it was happening in real life. And then finally, what's driving the power? Well, the silver and the number of turns is very powerful, and the thickness of the cable is very powerful. Now, how would you get this knowledge so clearly and so obvious through any other technique? Now what we're going to do is we're going to go back, and I'm going to create equations now for each one of those systems. So I've asked for a regression equation. Now what am I going to get? Well, now I get a regression table, and here it comes. Now on this page, now what we have here is a model for cost, model for energy, model for torque. I've now got a mathematical model so that I can see what's going on. Now let's do a quick analysis just to show you the power of the information that comes out of this DOE analysis. There's no other technique can work as well as this. So I'm going to draw a picture of one of the interactions. I'm going to draw the CD interaction over here. So 2 of the variables interfere with one another, they interact. So I'm going to draw the interaction. So CD, let's have a look, it's going to be thickness versus silver, so it's the wire, and you would expect these two to interact because it's the thickness of the wire and the percentage of silver in the wire. You would expect those two variables to interfere with one another. So if I create an exit and I let the graph get created, now that plane there, that twisted plane, that saddleback, that's showing you how this system behaves to thickness and silver content. Now it's just showing me how the power performs at this point. But if I go to a slightly different diagram, now this diagram, by the way, is just going to show you the edges. So it's going to show you the back edge, the front edge, and it's going to show you one line in the middle of that plane. So that's what the interaction plot is. So this is a much simpler diagram now. Back edge, front edge, and a section right through the middle. Okay, now then, how would I use the interaction plot? Well, of course, there's a couple of things I want to do. I want to be high. So the highest line, that light blue line, that's where I want to be, because I want to get power at the absolute highest. But look what happens if I go to the top. There's a great thing happens. If I go to the very top of that saddleback, the very point where it reaches the highest, I can also set a very wide tolerance. So let's go back to the whiteboard and we'll have a little look at this, and I can draw the diagram. It might be easier to explain. Let's go back to the whiteboard. Okay, let me just sketch that interaction line for you a second, because what it looks like is this. You've got a line that's going up and then topping out here, and of course here we're interested in, this happens to be power. Okay, so let me just show you the knowledge that's coming out of a designed experiment. And your computers can't do this. Your finite element analysis can't do this. Your computational fluid dynamics, they can't do this. They're not smart enough to know the context here. So this is knowledge that your skilled engineers and world-class engineering can only get together. So if you get this diagram, what's it telling me? Well, of course, I want to be at the tip here of this particular diagram. So this would be telling me, and I'm trying to remember what the thickness was okay, so this was thickness here. This is the thickness of the copper wire. So it's now telling me where to be on the thickness of the copper wire. Now if I have a target, so if we're here, there's a target, and we're going to make a promise. We're going to make a promise to the customer, and we're going to say, well, look, Mr. Customer, we're going to hit this target, and we will always make sure that the power is between this tolerance. Now look, if I take this tolerance across, look. Now look at this. There is your tolerance. It is telling me the tolerance to put on the thickness of the copper wire. And because I'm at the top, I'm at the peak of the curve, the tolerance is at its widest. I mean, look how wide I've made that tolerance. If I'd have made that spec that I'm promising the customer, if I'd have put it there, look how tight my tolerance would have had to be. But look how wide my tolerance can be now. Look at that. Now, if you can draw these pictures, with world-class engineering, you can smash the competition absolutely out of the water. Because what are you doing? You're providing the best performance with the cheapest manufacturing system. Because all your tolerances are really wide. Your defect rates will be really small. Your processes will just work sweet as a nut. Now, this is world-class engineering. This is design of experiments working in a design situation. Only world-class engineering can do this. Only design of experiments can do this. Any other technique is rubbish compared to this. Now here's the question. How many world-class black belts have you got working in your design department using world-class engineering every single day? Because that's what a black belt brings to your company. That's what Six Sigma is. So if you ever ask the question, where do I go next with Six Sigma? What comes after Six Sigma? I don't understand this. This is world-class engineering. It is sucking knowledge out of your designs and making you make more money. The next thing to do with world-class engineering, the next thing to do with Six Sigma is to make more money.